exemplar in this India. He also produced the first RDS in India. He also produced the first PM 2.5 in India. He also changed the micrometeorology monitor from flow recording techniques to the strip chart recording techniques to electronic data recording systems. So he is one of those rare person in the country who has taken a lot of effort and pains to develop indigenous instrumentation for monitoring air pollution. So he will give you a brief on the instrumentation available to meet this current requirement of air quality monitoring standards. Rakesh ji.
Thank you, Gupta ji. Can I have your attention please at the back? Can you people hear me? And what do we mean by them? I'm just going to take a few minutes, maybe 2-3 minutes of your time to try and bring this to your attention. Initially, the focus was on what was inhalable. So what could go into our body through the nasal tract or through the mouth, that was considered something which was of interest. And so a broad thing here that you see, 100 microns, I don't know whether you can read that figure there, but it was something like 100 microns which was felt that will remain suspended in the air, so residence time is quite large, and 2, it can also go into the body, and so it was of interest. But soon enough, as people in the morning have pointed out, it was realized that doesn't go very deep into the nasal tract, and so we started talking of what we started saying, thoracic particles that go below the larynx, and that's where PM10, what we later on started calling PM10, that came about. And if you look at the slightly darker curve here, somewhere here, now you find that it is a much smaller fraction of the total suspended particles. The maximum size that you see there is about 20-22 microns. So when we are talking of PM10, it is not a sharp boundary कि 10 से नीचे एक तरफ, 10 से ऊपर दूसरी तरफ. Everybody comfortable when I switch to Hindi? Yeah. I have friends from the south here. Comfortable? Okay. Glad to hear that. So when we say PM10, then we are not saying everything below 10 should come into my system and everything above 10 should remain out. The human body doesn't behave like that, nor does any physical separation device. Whether we use an impactor or a cyclone, anything like that, will have a efficiency curve, and that's what more or less this thoracic curve is showing. It is showing the separation mechanism of the human body, and the instruments that were supposed to be developed were supposed to mimic or conform as close as possible to this thoracic distribution. And so when we talk of PM10 samplers, then we talk of something which has something like 50%. If you look at this curve a little more in detail, I think I have another one which shows it a little better. If you just pardon me, I'll switch to another slide and then come back to this presentation in another minute. Okay. I think this one will show it to you a little more in clear detail. We are talking of this curve, and as you can see here, can you read this 50 at the back? So there is an efficiency curve which shows 50% efficiency of removal at something like 10 microns. So this was the thoracic distribution, and the PM10 samplers were designed for a slightly subset. You see it is going faster, it is decaying faster than the thoracic distribution, but still the Dmax or the maximum size allowable is something like 18 to 20 microns. We do expect something like 18 to 20 microns, maybe a few particles, but they would be present in what we call a PM10 sample. So this is an important point for you to bear in mind, that it is not less than 10 as the standard in lay terms has sometimes tried to emphasize. Nominally 10 microns. The standard has also got something less than 10 written in it. In that sense, it is a slight misrepresentation because it gives us the impression that everything below 10 should be part of my sample and everything above 10 should not be part of my sample. We do get some of these queries that how do I guarantee that there is nothing above 10? I don't. As an instrument manufacturer, I don't guarantee that above 10 nothing will be there, nor am I supposed to. The standard that internationally is accepted as PM10 allows a significant fraction of slightly larger particles to be present in what we call the PM10 sample. Please bear that in mind. Another thing that you should importantly understand is that we are talking of aerodynamic sizes. We are not talking of physical sizes. If you look at this particle under a scanning electron microscope or under a physical microscope, you might find it actually to be much smaller than the physical 10 microns that you are expecting to see. Because when you are having a separation mechanism, either in our nose or in a cyclone or in an impactor, then there are centrifugal forces at play. Because of the spinning motion in the cyclone or in the impactor trajectory or in the nasal trajectory, there are momentums and physical forces at play which are a function of mass, which is a function of density. So lighter material, physical size would be bigger and it will still behave as a smaller size particle. Denser material, say iron ore as compared to say charcoal. Charcoal density, charcoal even floats on water. Iron ore density much higher. Silica. So these materials, a physically smaller particle will behave like a 10 micron or a 12 micron particle. A lighter material, it might have physical smaller size, but it might behave, it might have physical larger size, but it might behave like a aerodynamically smaller particle. So when we are talking of size classifications, we are talking of aerodynamic sizes and it's defined by the settling velocity. I don't think my time permits you to go too much deeper into this, but those of you who have a little discussion required, you're welcome here, and we are here for about 2 days, so I'll be in touch with you if you have that thing to be answered. While we are on this slide, we may also resolve what are we calling as PM 2.5. So as Dr. Bhargav and some of our speakers in the morning have said, that soon enough the world realized that what goes much deeper into the nasal tract or into the airway systems is what is causing the health impacts. It is also a fact that the formation mechanisms of particles, finer and coarser fraction, where we are talking around 10 and around 2.5, the formation mechanisms are different. In the morning there was some talk of secondary particles and primary particles. So what is coming as dust from the roadside or from a crushing operation or what is released as fly ash from a chimney, that is a physical particle to start with. It has come about from a grinding or a crushing or a abrasive mechanism, something like that. Particle formation, when we are talking of secondary particles, ammonium sulfate or something which was a gas and then reacted in the atmosphere to form a particle, or something which nucleated, there were fine particles, nucleation, condensation, and that started forming the particle. So those mechanisms are different. Particle formation by crushing is a physical process. Chemical formation through reaction, secondary particle formation and so on. And so they found that the chemical nature of fine particles is quite different from the chemical nature of coarser fraction particles. Coarser fraction particles often had material which was less toxic, silica, coal, something like that. And so it was found that toxicity of the finer fraction is more, that is one, and it goes deeper into our airway systems, into the air exchange mechanism portion, and so as Dr. Bhargav pointed out, it also can end up into the bloodstream.